Hey guys, today I want to present a solution to the China National Math Olympiad 2024 problem 5. At first, let's take a look at the problem statement. We have given a prime number p, and now we want to call this prime number p good if we can find a bijection f from the set from 0 up to p minus 1 to the set itself, satisfying the following condition. If p divides a squared minus b for some a and b in a set from 0 to p minus 1, then we want that the absolute value of f of a minus f of b is at most 2024. The problem asks us to prove that we can find infinitely many prime numbers p such that they are good, and on the other hand, we can also find infinitely many prime numbers p that are not good. Since the equation a squared congruent to b modulo p is purely multiplicative, it's convenient for us to define g to be a primitive root modulo p. This allows us to rewrite the set of non-zero residue classes modulo p as the set of residue classes g to the power of 1, g to the power of 2, and so on up to the g to the power of p minus 1. Now we want to take a look at our equation a squared congruent to b modulo p. And in the best case, we want to write a and b in terms of g. But this is only possible if they are not equal to 0. And therefore, let's at first take a look at this equation if a is equal to 0. So if a congruent to 0 mod p, then we directly see that also b is congruent to 0. Otherwise, we have that a is not congruent to 0, and then we directly get that this is also not congruent to b. And therefore, we are indeed able to write these two variables in terms of g. Namely, we can write that a is congruent to g to the power of l and b congruent to g to the power of k, where l and k are positive integers. Moreover, the equation a squared congruent to b implies that g to the power of 2l should be congruent to g to the power of k modulo p. And now, since g was chosen to be a primitive root modulo p, this is equivalent to the fact that 2l is congruent to k modulo p minus 1. Now, 2l congruent to k is an equation much more convenient to deal with than a squared congruent to b. And therefore, we want to rewrite our problem statement in the following way. Namely, we want to say that a prime p is good if we can find an injection h from the set from 1 to p minus 1 to the set starting from 0 to p minus 1 in such a way that for residue classes k and l modulo p minus 1 with 2l congruent to k modulo p minus 1, we have that the absolute value of h of l minus h of k is at most 2024. Giving such an injection h, we can define f of g to the power of l to be equal to h of l. And f of 0 is defined as the value that h does not attain. And we can also do this the other way around, and therefore our two definitions of good are the same. So let's erase the board and try to work on the new problem statement. We want to think about this problem as a graph, such that k is connected to 2k, is connected to 4k, and so on, such that we connect exactly those vertices k and l, for which we want that h of k and h of l are close together. To make it more precise, let's define g to be the graph with vertex set v and edge set e, and the vertex set v should be equal to the set of residue classes modulo p minus 1, so v is set over p minus 1 set, and the edge set e is defined as the set consisting of all unordered sets v, 2v, 4v in v. Let's get back to our picture and try to figure out more about this graph. We can go along this path, and in each step we can double the coefficient in front of the k and give it to the next vertex. This will go on until we end up at a vertex 2 to the power of t times k that is connected to one of the previous vertices. Now we are interested in finding out the exponent t. For this, let's consider the equation 2 times 2 to the power of t times k is equal to 2 to the power of r times k. And here 2 to the power of r times k should be the vertex where the circle gets closed. For convenience, let's at first consider the case that k is co-prime to p minus 1. And in this case, this equation here is equivalent to 2 to the power of t plus 1 equals 2 to the power of r. We want to have a notion for how many times an element x in V is divisible by 2. And therefore, we use the definition that for x in V, nu2 of x is defined as nu2 of the greatest common divisor of x and p minus 1. I want to note that this greatest common divisor is a divisor of p minus 1, and therefore nu2 of this quantity here is less than or equal to nu2 of p minus 1, and I want to call this r prime, so I define nu2 of p minus 1 to be equal to r prime, and this also allows us to write p minus 1 as 2 to the power of r prime times s, and s is odd. Now let's come back to our picture here. And we see that in the beginning, in each step, nu2 of our vertex is increasing by 1. This goes on until we reach one vertex, such that nu2 of this vertex is exactly equal to r prime. From there on, nu2 of our vertex stays equal r prime. And therefore, we directly get that this r here is greater than or equal to r prime. This allows us to divide both of these sides here by 2 to the power of r prime to get 2 to the power of t plus 1 minus r prime is congruent to 2 to the power of r minus r prime modulo now s, because s is equal to p minus 1 divided by 2 to the power of r prime. If r would be greater than r prime, we could decrease both t and r by 1, and this equation here is still true because s is odd. Since t was minimal satisfying this equation here, we know that r is equal to r prime, and therefore we can erase all the primes here. We especially get that the right-hand side here is equal to 1, and since t was minimal, this directly implies that the exponent here is equal to the order of 2 modulo s. In other words, we get that t equals order 2 of s plus r minus 1. We can generalize this approach here for an arbitrary residue class k that is odd. And for this, we want to define s prime to be s divided by the greatest common divisor of p minus 1 and k. Our first step now holds for all k odd, but our equation here is that 2 to the power of t plus 1 congruent 2 to the power of r modulo p minus 1 divided by GCD of p minus 1 and k, and thus we have to replace s by s prime everywhere else. We now understand the cycling behavior of our graph, and it is left to fully characterize our graph, which I want to do now. As we figured out, the length of the path here from an odd number to the circle is equal to r, and the length of the circle is then the order of 2 modulo s prime. Let's try to understand the rest of this connected component here. And at first, I want to mention that since k is odd, it only has one neighbor, namely 2k. For 2k, we have one more neighbor, namely 2k is connected to k plus p minus 1 over 2. In general, odd vertices can only have one neighbor, and even vertices have at most 3 neighbors, namely 2 times this vertex and the vertex divided by 2, which gives us 2 residue classes. Let's use this knowledge to draw in all the other vertices of this connected component. I want to note, if we take one of the vertices in this connected component with distance d to the circle, then nu2 of this vertex is equal to r minus d. Moreover, if this distance d is positive, then this implies that the vertex has exactly one neighbor with larger nu2 value. This implies that all of the arms we get here are disjoint. Now we are ready to finish the proof for our problem. And at first we want to consider the case that we can find such an injection H. In order to find such an injection H, it would be convenient if all the arms here were as short as possible. And indeed, we can get this by choosing r equals to 1. So let's consider P congruent to 3 modulo 4. By our previous observations, we know that in this case, one connected component consists of one circuit, where each vertex in the circuit has one more neighbor outside the circuit. Moreover, we know that all these neighbors are distinct. Our strategy for constructing our injection H is to consider a pair of adjacent vertices in our circuit and give them the values 0 and 2. Now we go along both directions on the circuit and alternatingly assign all the even values to the vertices. So this vertex should be 4, then here we want to have a 6, and the last one should be 8. We can easily see that by this construction, the difference of two adjacent values is at most 4. And now, for the vertices outside the circuit, we just take the value of the neighbor and add 1. So we have 1, 3, 5, 7, and 9 here. This gives us a valid labeling for one of the connected components. And now we can just go on to the next connected component, start with the value 10, and go on with the same strategy. Hence, we figured out that in the case that P is congruent to 3 modulo 4, we are indeed able to find such an injection H. So this case works. And now we can use Dirichlet's theorem, which tells us that there are infinitely many primes P congruent to 3 modulo 4. And therefore, we indeed found infinitely many prime numbers P, satisfying the condition that they are good. We are left with finding prime numbers P that are not good. And from this idea here, we can see that if the arms are not too long, then we are always able to find a similar construction to this one. And therefore, we know that if P is not good, the arms here should be very large. If one of the arms here is very large, then we know that some of the values of the vertices in the arm must be far away from this original vertex here. Having only a few number of such arms next to each other, this should be no problem. But if we have several such arms next to each other, we can indeed bring this to a contradiction. If we are in the case that the order of 2 modulo s is greater than or equal to 4040 and 9, we know that we can find all the vertices 2 to the power of r, 2 to the power of r plus 1, and so on up to the vertex 2 to the power of r plus 4048 in one circuit, and all these vertices are distinct. Let's consider one of the vertices 2 to the l, where we want to have that r is less than or equal to l less than or equal to r plus 4048. Since the h value of 2 to the r to 2 to the l changes by at most 2024 in each step from 2 to the r to 2 to the l, we know that their difference, so h of 2 to the r minus h of 2 to the l, in absolute value is less than or equal to 2024 times 4048. In other words, we know that h of 2l is an element of the set h of 2r minus capital P, where capital P should be this product, up to h of 2r plus capital P. Moreover, all the h values of one arm have to stay in the set, or they will at some point attain one of the 2024 values before h of 2 to the r minus p or after h of 2 to the r plus p. Since these are only 4048 values, but we have 4049 disjoint arms, we know that we can find one arm which only attains values inside the set. This implies that on the tree, h can only attain 2p plus 1 different values. But from here, we clearly get a contradiction, if we take r to be equal to 2p plus 2. We can indeed achieve this by taking p congruent to 2 to the r times z plus 1 modulo 2 to the r plus 1 times z, and here z should be equal to 2 to the power of 4049 plus 1. Since z is odd, this indeed yields that nu2 of p minus 1 is equal to r. Moreover, we know that s is a multiple of z and therefore greater than or equal to z. And this implies that the order of 2 modulo s must be at least 4049. Hence, we are exactly in this case where we can prove that p is not good. And thus, it is left to show that we can find infinitely many such prime numbers p. But this directly follows from Dirichlet's theorem, since these two numbers here are coprime. And therefore, we are done.